Okay, the next thing we're going to cover, we're still in section 17.3 of chapter 17. It's a titration of a weak acid and a strong base. So again, on the titration curve, this is just a picture of one from your book. If you plotted the pH on the y-axis versus the volume of sodium hydroxide added, it has a similar shape. But typically when you're doing a weak acid, y'all know that a weak acid means it does not completely ionize. So that means that the pH that you start with is going to be higher than an acid than if it were a strong acid. If they were both the same concentration, a weak acid is going to start with a higher pH. Also, this is an important thing to note. The equivalence point of a weak acid strong base is not at 7, okay? It's above 7. Because if you'll remember when we were talking about the pHs of salt solutions, if you take a weak acid plus a strong base, the salt that it makes is going to be a basic salt. In the previous titration, we did a strong acid, strong base. Those make a neutral salt, but this one makes a basic salt. So the calculations we're going to be doing in this weak acid, strong base titration, y'all, they're all calculations you've already done before. It's just the questions are asked in a different context. We are still going to, I'm going to show you how to calculate like an initial pH where it's just acid. We're going to calculate, I'll just pick here, but some point in here before you reach the equivalence point for B. We're going to calculate C, the pH at the equivalence point, and then we're just going to pick some point up here. I'll just label this one and calculate D. Okay, this is the problem we're going to work, so you may want to pause it for a second to write it down, and then after you get it written down, start it back up and listen. Okay, this process would produce the titration curve on the previous slide. We're going to take hydrofluoric acid, 15 milliliters of it, and we're going to start with just the acid. So the first thing we're going to do is calculate the initial pH of just acid. Then we're going to add some KOH and calculate a pH, and I left this blank because I want you guys thinking about it. B, if you look at the titration curve, B, we need to pick some point before the equivalence point. Do you guys know the equivalence point? How much KOH will have been added at the equivalence point? You should know that that means there's also 15 milliliters of KOH. Because if the acid is 0.1 molar and the base is 0.1 molar, then they are going to be at the equivalence point when you have 15 milliliters of both of them. If they weren't both 0.1 molar, then you could do M1V1 equals M2V2 to figure out what the equivalence point is. So typically what I do here is say what volume do you want to use on B, and I'll let the class pick the volume. But what I'm trying to get y'all to realize is it's got to be it's got to be above 0, but less than 15. And so we will do, we'll just pick 12 since I don't get to hear what you guys say. Then what's going to be the pH after the equivalence point? Because on our graph, if I go back, D is after the equivalence point. So y'all, it just needs to be above 15. And so we'll just do 17 mils. Okay. Because this is a weak acid, weak acids have a Ka. So I'm going to look that up because we're going to need that the whole time. The Ka for hydrofluoric acid is 7.1 times 10 to the minus 4. So I'll be using that number a couple of times. Now, you know how to do A, you just haven't seen it asked in the context of a titration. A, how do you calculate the initial pH of the acid? Pause and think if you need to, but hopefully you guys will remember that the Ka is equal to x squared divided by the initial concentration of the acid minus x, that x is really small. So I'm going to say 7.1 times 10 to the minus 4 is equal to x squared divided by 0.100. And I'm going to solve for x. When I solve for x, x is equal to what? X is going to be equal to the hydrogen ion concentration. How do we know that? Because anytime we start with a Ka, x is equal to the concentration of the hydrogen. So for x, I got 8.43 times 10 to the minus 3 molar. And how do I get the pH? I take the negative log of that. And the pH is 2.07. Okay? So that's a weak acid. What if this had been a strong acid? What would the pH of point... This is just kind of a little side note here, just to drive home what I'm teaching you. What if it had been 0.100 molar strong acid? What would that pH have been? If it were a strong acid, you just take the negative log of 0.1, and the pH would have been 1. So I'm pointing that out to remind you, when we looked at that graph, if you have the same concentration of a weak acid versus a strong acid, the weak acid, the graph's always going to start at a higher pH. Okay, but that's the work for part A. Now, for part B, we've added 12 milliliters of strong base. So I want you to write a reaction for HF and KOH. And then start it back up and check what you wrote. Okay, hopefully you knew to write hydrofluoric acid plus potassium hydroxide yields potassium fluoride in water. And both the hydrofluoric acid and the potassium hydroxide are 0.1 molar. We're at part B. And in part B, and throughout the whole titration, y'all, we have 15 mils of HF. We always have 15 mils. That's not changing. What we're changing each time is the KOH. And for B part, we said we would do 12 mils of KOH. Do you know, by looking at those numbers for a second, do you know which one's the limiting reactant? In other words, which one are you going to run out of? You should recognize that you'll run out of that one first. If they're equal concentrations, but you have less volume of this one, that's going to be the smaller number of moles. Therefore, you're going to run out of that one first. Okay? But we do have to figure out how many moles we have. Do you remember how to get moles? That molarity is equal to moles per liter. So the molarity times the volume in liters gives you moles. So let's figure out moles of each one. So it doesn't matter if you put it in scientific notation or with decimals. 0.0150 moles of HF and 0.0012 moles of KOH. And so if we were doing an ice table, which we're going to do because it shows you what's going on, we already said that the KOH is the limiting reactant. So we already knew before we did this that we were going to run out of it, but we can see that now because I have less of it and they're reacting in a 1-to-1 ratio. So, this is going to be an equilibrium reaction. I didn't put that equilibrium arrow to start with, but it is an equilibrium because it's a weak acid. So I know that at equilibrium, I'm not going to have any KOH. If I start with 0.0012 and at equilibrium I don't have any, then I know I'm going to use all of the KOH. And remember, that change line, once I know one number on that change line, I can figure out all the other numbers. Water's not going to matter because it's a liquid, and of course I started with 0 of this. So then I just do that math. So I need these numbers. I need these equilibrium numbers to solve the problem. What do we have here? When we add 12 milliliters of KOH to 15 milliliters of HF, both at an equal concentration, we end up with some of the HF left over because it didn't all react. But we also have some of the salt formed from this reaction. Guys, do you see that what you have left over is a weak acid, HF, and its conjugate base is what's left over because the fluoride is the conjugate base of the HF. Remember, potassium's a group 1. It's a spectator ion. It's a group 1 metal. It's not going to matter for pH. What I'm trying to get you guys to see is what you have as a buffer. And we have an equation to use for buffers, the Henderson-Hasselbalch equation. The pH is equal to the pKa plus the log of the concentration of the base divided by the concentration of the acid. If you'll recall that pKa is the negative log of the Ka, and we took the Ka earlier, is 7.1 times 10 to the minus 4. So the pKa is 3.15 plus the log of the base concentration divided by the acid concentration. And I get that the pH is 3.75. Okay? Now, more I want to say about this. Y'all, these square brackets around the base and the acid, y'all know that means concentration. That means molarity. Did I plug the molarity in? I did not. I plugged in the moles. How do you get molarity? Molarity is moles divided by liters. Mathematically, it does not matter in this equation because technically the moles of the base is 0.0012 moles divided by, I just totally forgot how to add, divided by 0.027 liters. Now look for a second and tell me where 0.027 came from. It came from the total volume, the 15 plus the 12. So 0.0012 divided by 0.027 means the molarity of the base is really 0.044 molar. But I also have to divide the acid by 0.027. So the molarity of the acid is really 0.011. And if you did the calculations with those numbers, you get the same answer because of math, because you've divided them both by the same number. But we still get 3.75. So I'm doing all that to say you can just use the moles here, because if you didn't, you're going to ratio them the same. But I didn't want there to be any confusion over the fact that y'all know that square brackets means molarity, and you know that the ice table had moles. Okay, so when we do this, we're thinking. In B part, y'all, the pH in B, I'm going to go back a few slides, it had to be higher than the pH in A. So watch it and make sure that's happening. Okay, if A's pH is 2.07 and B is 3.75, that makes sense. We've got to go up. C, we've got to go up even more because we're going to add even more of the base. So I'm going to rewrite this balanced equation with my information under it to solve C part. So you guys pause the video and set all that up, and then start the video and see if you have what I have. Okay, so at C, we're at the equivalence point. And so we knew that at the equivalence point, of course, we're given the concentrations in the problem. We knew they were both 0.1 molar. But at the equivalence point, we had to recognize that that meant 15 mils of KOH. So if we did an ice table, what that means is we have 0.0015 moles of HF. Remember, the molarity times the volume in liters gives you moles. 0.0015 moles of KOH. Those are the same number because, see, that's what an equivalence point is. An equivalence point is when all the acid and when all the base have been used. Okay, you've added equal moles of both. Okay, the water doesn't matter. Okay, so at the equivalence point, all we have is salt water. But this salt is the salt from a weak acid and a strong base. That means, we talked about it at the beginning of this problem, this is a basic salt. Why is it a basic salt? It's not the potassium that makes it basic, it's the fluoride that makes it basic. Can you guys write fluoride ion, a balanced chemical equation, fluoride ion in water, and show me what the fluoride does to make it a basic salt? Pause it and write it. It's a basic salt because the fluoride ion takes a hydrogen from water. The fluoride ion takes a hydrogen from water, leaving water with the hydroxide. That's why it's a basic salt. Okay, so in this one, the fluoride ion, if we did an ice table, we're starting with 0.0015 moles of the fluoride. The water doesn't matter. Of course, we don't start with any HF or OH. How much of the fluoride is going to get used here? We can't say all of it because it's the conjugate of something weak. If it was something strong, it would be all of it, but it's not all of it. So it's X. That means we're going to make X HF and X amount of OH as well. And this is an equilibrium reaction. So if we write an equilibrium constant expression, K, it is equal to products over reactants raised to the power of the coefficient. So see, the HF is X. The OH is X. And the fluoride ion concentration is 0.0015 minus X. We're going to get rid of that minus X. But in this one, it matters. We have to enter the concentration of the fluoride. So we can't, what do we have to do? The 0.0015 to get the concentration of the fluoride. We have to divide it by the total volume. What's the total volume? The total volume is 30 milliliters, so that's 0.03 liters. That means the concentration of the fluoride is 0.050 molar. And so that's the number we got to put in over here. What's the K? This is not a Ka. For it to be a Ka, this is the Ka for HF. You have the HF on the reactant side. since the HF is on the product side, it's not a Ka, it's a Kb. How do we get Kb? Kw divided by the Ka is equal to the Kb. So calculate that. And so for the Kb, I get 1.41 times 10 to the minus 11. And I'm going to solve this. Ooh, my pen just skipped out on me. I'm going to solve this for x. For x, I get 8.39 times 10 to the minus 7. What's the negative log of that? It's going to give us a number, obviously, but what is that number telling you? The negative log of that gives me the POH. How do I know that? Because if I use a Kb, X is always equal to the hydroxide ion concentration. And so to get the pH, I've got to subtract it from 14. And the pH is going to be 7.92. And that's part C. Now I want you to set up a reaction for part D. Okay. This should be the same reaction that we used in A and B and C. We didn't use it in A because it was just acid. We need to get moles. We got our molarity and volume. We need to get the moles out of each one. So the molarity times the volume in liters will give us moles. Okay, which one's the limiting reactant? We knew that we had neutralized all the acid because this one was past the equivalence point. And that should be how we complete the ice table. So, past the equivalence point, what we have left over is strong base and the basic salt. Okay? The basic salt, even though there's more of it past the equivalence point, it's a weak basic salt. So the pH at this point at part D, the pH is only going to depend on the strong base. So we need to figure out the concentration of the strong base. To figure out the concentration, we take the moles of the strong base, divide it by the total volume, which is 32 milliliters. So the concentration of the strong base is 0.00625 molar, and that's the strong base. And so the POH is the negative log of that. The POH is 2.20, and so the pH is 11.8. Okay, so there's another one of those weak acid strong base, like I said, worked in your book. It's a different one from what I worked, okay? It's worked in the book. There's another, you can find a YouTube video, I think, of me doing a weak acid strong base. Maybe it's a different one. Maybe it's not the HF and the KOH for practice. But it seems like a lot right now. These calculations aren't new, okay? We've already been calculating, like in C, the pHs of salts. We've already calculated buffers. We've already used this formula in Chapter 16. Let me kind of summarize something for you on this slide, okay? You know how to do Part A, okay? When you're doing a weak acid, and that's all you have, it's Ka is equal to x squared divided by the initial concentration. anywhere in here, anywhere before the equivalence point, you are going to have to use the buffer equation. Okay, I'm just going to write B and A for base and acid. Always the buffer equation there. At the equivalence point of a weak acid, strong base, you've got to jump from the Ka to the Kb. Okay? You're going to have to do the Ka to Kb. You're still going to need to do the ice table to figure out how much of the salt do you have and do the concentration. Okay, for part D, it's going to be just worrying about the strong base. So you just need the concentration of the strong base, just like we did at the beginning of chapter 16. Go from there to POH and then ultimately to pH. This one may take you watching it again, but it's also going to take you practicing some of these. So practice some of those. There's sample problem, let's see. Sample problem 17.4 in your book is one that is you could practice, and it shows you how to work it. The book does. And of course, when we do another web conference, guys, and get online and we can talk to each other, I can work another one of these with y'all. So that does not finish chapter 17, but that gets us through a lot of the acid-base stuff. Those are the only two titrations I'm worried about you knowing. A strong acid, strong base, and a weak acid, strong base. That's the only two that I'm going to focus on.